Okay, you all are pretty well prepared here. Uh, Now, in a couple of cases, uh, people tried to solve this equation using the techniques of linear equations, and I kind of had to remind you, no, this is a quadratic equation. And of course, you need to recognize that. When you see that x squared and that x term and that number, you know it's quadratic. Okay, so let's first find the zeros of this. Now, once you find the zeros of this, people did real well doing this the hard way. I think everybody did it the hard way. And I'm not sure what everybody did on this, but everybody was starting by finding the zeros, which is an excellent start. Okay. Then I decided to write a bunch of stuff out on the board. So I wrote out the obvious stuff I'm pretty sure everybody knows. So we can talk about the little finer points that you want to put on this. Okay, so solutions to the equation. Well, the zeros, what do we mean by the zeros of a function? Well, those are the solutions of the equation f of x equals 0. In other words, whatever the function is, you set it equal to 0. Everybody immediately did that. And then, you know, you try to rearrange it with the x's on one side and the numbers on the other side. And that doesn't work out because you never get x. You get an x squared plus a or minus a 3x equals some number, and you're stuck. Okay, you're stuck until you realize that it's a quadratic equation. So the zeros are out, x equals negative b plus or minus and so forth. And a lot of you knew that formula. Okay, and that's good. I think I know I mentioned in class, you know, went to pretty highly selected school, science and tech school. And I was kind of in the upper third there. Really not a whole lot higher than that because very selected. And I was put into a calculus class with an actual professor instead of a grad student. A lot was assumed in that class, but I realized that more than half the class didn't know the quadratic formula, which kind of shocked me. You know, everybody in that class is probably in the top 2% of their high school graduating class. I don't know. So when you talk about how much better things were in the old time, okay, can't really use that as an example. And the point of that is that top-notch students were coming to college not knowing the quadratic formula back in, what was it, 1843 or something like that. And it was 1965, but right in the heart of the space race and everything, strong emphasis on math and science, not everybody knew. So if you didn't know it coming in, if you didn't know it coming in today, even having used it in the assignments, you knew what to do with it as soon as I wrote it down, and you pretty much knew what the formula was. But it just said write it out, think what somebody would have. Okay, so it's looking pretty good. You're well prepared on this assignment. So we're just going to look at the finer points. Okay, so I'll stop talking. Let's do it. I'm going to talk while I do this. F of x equals 0. So that means x squared. In my case, it's not in my case. The numbers are actually different. Okay. Let's just say this was the function that somebody got. Okay. So you would do this, and you immediately recognize this is ax squared plus bx plus c. A, B, and C have these obvious values. You write the 1 before you write the 2. And then you get 12. Okay. You write a minus in front of the 2, you got no places to put 1. Okay, so we have these obvious values, and then the quadratic formula, we need to use it correctly, is negative b, which is a negative of negative 3 plus or minus b squared of negative 3 minus 4 times a times c. There's a minus 12 on the root of that this time, over 2 times a. Well, that works out to 3 plus or minus the square root of, that's going to be 48, that's going to be 9, so that's going to be 57 over 2. I'm going to write that as 3 halves plus the square root of 57 over 2. And that's then be approximately equal to 3 halves plus or minus. Okay, 57 is between 48, 49, and 64. Squares of 7 and 8, somewhat closer to 8. So I'm going to guess that that would be 7.6. And since I'm writing this out as a decimal approximation, might as well write my 3 halves as a decimal approximation. Of course, not an approximation in this case, it's exactly right. So it's 1.5 plus or minus 3.8, which equals then 5.3 or negative 2.3. So I should then say the solution set is a set. Probably we're going to the lesser number first. So I started with the 5 on this continuum, but should be negative 2.35.3. We usually put them in order because you've got a bunch of solutions and you're looking for one of them. It's easier to find it if they're in order. If there are only 2 of them, you're going to see them both anyway. Still should have followed standard procedure. Not wrong if you write it out in a different order, random order, whatever. Easier to see what's going on if you're doing it in this order. And I'll note a couple of other things now. What's the axis of symmetry? If we want to graph that, I didn't ask you to graph it, but what, how do you find the axis of symmetry? Let's talk about it for a minute, see if people know. Okay, I've said a lot of stuff and I apparently haven't recorded, which is too bad because there's a lot of good stuff. But what we're doing right now is talking, first of all, about graphing this function. We graph this function by, well, we find the zeros. We find the axis of symmetry, we find the y-intercept, we get a graph. We can expand this into this so we can use a quadratic formula. The quadratic formula, we get the axis of symmetry, 6 over 2 is 3. We get the fact that there are no real solutions because we have a negative under the radical. And we find that the vertex occurs. First, the y-intercept, we plug in 0 here, and we easily get 16. The vertex occurs when y equals f of 3, plug in 3, we get 7. So we've got all the information we need. So this is one way to obtain the graph. And the graph ends up looking like this. But the way I constructed this graph was using transformations. This function is a basic squaring function, horizontally shifted 3 units because x is now x minus 3 and replaced by x minus 3. And then we've added 7, which gives it a vertical shift of 7 units. In this form, we still get the y-intercept. We let x equal 0, we get negative 3 squared, which is 9, add 7, we get 16. So we get all the information we had before. we can take our basic squaring function. Now, when I do this, I just started with the origin here, because that's our vertex. We shifted 3 units horizontally, 7 units vertically, because that's exactly what the transformation model tells us to do. We got the origin. So we know that the parabola is going to have its vertex right here on the axis of symmetry, which is x equals 3. Now we've then filled in some points. Once we see that this is 3 and this is 7, well, now we've got a scale for the x-axis. 3's here, 7 here's on the y-axis. And then we can say, okay, 1, 1, well, about 1/3 of this distance be about here, 1/7 of this distance be about here. So I just said, okay, that's about where 1, 1 would go. This would be -1, 1, then 2, 4, -2, 4 should have been a little higher. But then we take this and we just transform every one of these points. And we're going to get points that, like this. We can draw a little curve through those points. And there's a pretty good representation of the graph. And if we also take into account that the y-intercept is 16 and make the graph a little higher, we put a y-intercept up here at 16. We see this very plausible that this will cross the y-axis around 16. Okay, now, we then said it's taken off of this. That's a process. That solves the problem of graphing. We can easily solve this equation. It's much easier than using the quadratic formula. Because all we have to do is add -7 to both sides. We get x minus 3 squared equals -7. X minus 3 plus or minus the square root of -7. Square root of -7 is not a real number, so there are no real zeros. Well, this is the function we just graphed. And you see there are no real zeros. This thing does not go through the x-axis. Okay, well then, it follows that the graph doesn't intersect the x-axis. And that's exactly what we just pointed out. Okay, taking off on this a little bit for comparison, we're going to look at x minus 3 squared minus 7 equals 0. So we add -7 or plus 7 to both sides. We get this equals 7. Take the square root of both sides. Yeah, but remembering that it's a plus or minus over here, because when you square the negative of square root of 7, you still get 7. So we get plus or minus square root of 7, which is plus or minus 2.7 roughly. Then we add 3 to both sides of this. We get x equals 3 plus or minus 2.7, 0.3 or 5.7. Now, this is a transformation. Okay. First of all, we can graph by I'm going to go through the whole process. So again, if we start with a basic squaring function, we can graph this expression by, again, recognizing that x is shifted 3 units horizontally and y is shifted, the y coordinate of any point on the basic squaring function is shifted 7 units downwards. So in this case, we shift over 3 and down 7. So our vertex is going to be here. This is the vertex. This is the shift of the transformed vertex. Then, now we have a scale. Okay, we can see that. Okay, let's see. One should be about here, here, and then 2, 4, and be up about here. -1, 1, -2, 4 might be here. So these points would transform. Maybe here, and here, and maybe here, and here. Okay, so the graph, it looks like this. Now, what's the y coordinate of the y-intercept? I'm going to pause for a second and let you tell me. Okay, so we just asked, how do you get the y-intercept? You let x equals 0. X equals 0, you get 0 minus 3 squared, that's negative 3 squared, which is 9. And then you subtract 7, you get 2. So the y-intercept should be f 0, 2, which should be about here. So then we could say that yeah, it's very plausible that this graph goes up, intersects the y-axis here. Okay. And if it does intersect the y-axis here, it's still positive when it crosses the x-axis. But it's pretty close to 0, right? Was that consistent with our solution set? Well, yeah, our 0, we have a 0 at x equals 0.3. Okay, by the way, equation, approximately 0.3. Anything. We have 0.30 here. Now, this is 3. Is it plausible that's 5.7? Well, I might have made it a little too fat. 3 here, 3 here. Looks like it maybe sits a little over on the graph, but that's pretty close to 5.7. And right there we have the graph. Okay. Now, if you put all this together on quadratic functions, I think there's a very good chance you can because you're real well prepared today. You know, a few little glitches that we talked about earlier. You know, recognize when you have a quadratic equation, so you use the quadratic formula. And if you have an equation like wherever it is, like this, instead of expanding it and using the quadratic formula, which works just fine, gave us negative 12.8. If it's factored already, well, the only way a product of two numbers can be 0 is one of them 0, maybe both. It might be the same. Okay, you can't find two numbers that multiply out to 0 unless one of them at least is 0. If they're both 0, it's still 0. Okay, so we could write this equation and break it down into two equations. X minus 8 is 0, x plus 12 is 0. And we find that x is 8 or x is negative 12. Make sense? So our solution set is negative 12.8. Anyhow, that's pretty much a summary of everything we did. It gives you techniques that you need. Now, there's also an assignment on applications of quadratic functions. What most of those come down to is, okay, if here's your quadratic function that represents the profit of a business versus the price it charges for its product. We've talked about that, haven't we? You get a curve that looks like this. You got the x-axis here. Where that curve crosses the x-axis is where you get 0 profit. Okay, so that curve peaks is where you get your maximum profit. And if I tell you what you're charging, you just plug that into your quadratic function and find how much your profit will be at that price level. That makes sense? Okay, good.